Minsky is a new entrant into a rather crowded marketplace called system dynamics modeling software, or system engineering modeling software. And what I want to do now is compare it to some of the much more developed rivals that it has. Of course, I'd never have developed Minsky if it weren't rating in the Godly table, which is something that the other systems don't have, and I'll explain why that matters so much in the next video. But this is the Minsky interface. You've seen how we define equations in terms of flowchart equation, which is, I'm going to compare like for like here, so I'll look at that side of these programs, that side of Minsky as well. So you define such objects by clicking on the integral block down here, labeling it. You can give a variable. The variable is always attached to an integral block, which is something you'll find is not common. And therefore this particular equation, reading it backwards, says the rate of change of x is a multiplied by y minus x. That gives you a way of building a dynamic model, and then of course doing the simulation, which you see on screen at live, and you can vary various elements of the system by changing parameter values and so on, and see what happens, and etc. etc. Okay, so that's a program which has had about 2,000 hours worth of programming time put into it. This, on the other hand, is the market leader. This is Simulink, which is part of MATLAB. If you wanted to buy a copy of this as an academic, you'll be setting yourself back $1,500. You're going to buy commercially, I think you'll be setting yourself back out 10 times that much. And it dominates engineering, both in terms of education at universities, and also then when engineers go and work out in the real world, they almost always buy a copy of MATLAB and Simulink to do their modelling in. Now, it began a lot earlier than Minsky, obviously, also earlier than Vensim, which I'll show in a moment. So it began with the whole idea of, as Forrester first originated, building a complex model by wiring together components. So I've wired together the Lorentz equation, so I can compare it to what I've got over here with the Minsky program. But one thing it doesn't have is the idea of variables. As I've said, I've got over here with x, it's actually attached to the integral block, and the variable x can be placed anywhere else on the palette. If you want to use it somewhere else in the system, you just drag it down, and then whatever signal is turning up at the x level for the system turns up where you put it in the system, whether that's a graph or an argument to another equation and so on. Simulink doesn't support that yet. It's got a simple idea of this, I think, which is where you can use a numbered label to transfer a signal from one place to another. But to actually say this is x and put x somewhere else in the system, no can do. What I've done here is I've labelled this particular integral block as x by typing the text string inside here, but I might as well call this Fred for the impact it has upon the system itself. But x then links back here via the wire, so that x is now part of its own definition, the rate of change of x, and x is also involved in defining the rate of change of y, and x is involved in defining the rate of change of z. So in one sense it does let you see the actual flows running through a system, and in terms of a circuit diagram way of thinking about the world, this is extremely useful. But when it comes to a complex model, I think it actually makes it harder to read what's actually going on. So stage one of where I think that what we're doing is an improvement on what you get in Simulink. The second thing is, notice I've got these things called scopes down here, and scope 2 is named over here and scope over there. That's the way you see a graph. You can't actually embed the graph, at least as far as I'm aware. You certainly couldn't last time I had my good mate Tron Andresen take me through using Simulink. But it doesn't support embedding a chart inside a system. So to see the results, you've got to have them in a separate window. Okay, I'm waiting here. This may be because oh, there we go, good. Okay, so you see the simulation result down here. I know that Tron has shown me the simulation is running live with time, so it's just my inexperience to show that I can't actually do that. But certainly not being able to embed the diagram, the chart in the diagram, I think makes it less visually appealing, less interactive than what we've done with Minsky. So that's the market leader in systems engineering. In systems dynamics, pardon me, I come over here. This is the market leader, called Vensim. So most people who work, from what I understand, this dominates the people who use system dynamics in marketing or management, in ecological studies as well. I think the World 3 model, the famous forester model, was developed in a predecessor to Vensim, and you can now find it in Vensim. Now, Vensim, again, it's the same basic idea. Here are blocks up here, which I haven't actually set this model up. I just copied this from another site, so it's not one that I actually built, whereas I did build the one you saw a moment ago in Simulink. This is X, Y, and Z variables. Sigma, A, B, and R are the terms it uses for the same reason I'm using A, B, and C in my model. And notice how X is the variable. How do we take a look? Well, you've got to click inside. And I don't know why they do this, but the first thing you can do is change the font. I don't think that's all that useful, but I might as well change it anyway. You want to see the equation, you have to click on here. And what is the equation for X? Well, it's the integral of dx. Initial value of initial x. So let's check and see what the dx equation is. That's down here. And the equation for dx, it's sigma y minus x. Now, call me picky, but I don't regard this as a visual interface for writing equations. It's very much form-driven. You know, you have a box to put the equations in, but you write the equation in exactly the same way you would if you're writing a program in BASIC or in another computer programming language. It's not truly visual. Yes, there are visual effects there, but to actually see the visual flow, you need something either like what is provided by Simulink here, or what, pardon me, come over here, or what we're doing in Minsky. And also, I can't work out how to do it from this model. I don't think it actually is possible to do the simulation other than see the final result. You can't see, as you can in Minsky, you can't see the simulation running through time. You can just get a different simulation each time given whatever parameter values you feed in. So let's go across to the final program we're going to take a look at. And this is the one that I regard as in some ways inspiration for what I've done in the visual side of Minsky, though I'm trying to do better in some ways. This is Vensim, which also has a very significant market share in the engineering world. And for a start, the equations, just as I've shown you with Simulink, are done visually. That's a multiply block. So here's our equation for x. This says x is the integral, and that's this. Oh, by the way, the 1 over s symbol is something which engineers would be familiar with. That's a symbol that implies they're using what's called a Laplace transform to convert a differential equation into an algebraic one for getting a solution. So they use 1 over s. I prefer to use the integral of something with respect to time explicitly because that is something economists just aren't as well trained as engineers in mathematics. So it's much more straightforward to say we're actually integrating a flow there rather than saying we're doing a Laplace transform as the generic approach in engineering software is. But let's take a look at it. This says x is the integral of, what have I got there? I've expressed this one I think I defined some time ago, but I'm looking how I've multiplied it. I've got a times x. I hope I've got the logic right there. Not quite as easy to read, but that's probably my fault rather than the program. So I've actually, what I could do perhaps is just pull that out of here and attach that to y times x up there, and then delete that particular variable. It's a times y minus x, isn't it? Okay, let's just fix that up a bit. Okay, so I've got y minus x there. I think you can see that even I've made a stuff up in setting this model up from some time ago. It's fairly easy to edit. So it's y minus x there. Drag this back. Pull that wire away. This is context sensitive, as you can see. It works that if I put my pointer here, it's ready to connect a variable together. If I put it on a block, it's ready to move the block. If I take a few elements like that, then I get a right click to choose whether I'm wanting to align things or cut. So it's a very complete user interface. I think it's the best of the user interfaces there. And when you simulate the model, I've got it defined properly, you see it live, and you can embed, as you've seen I've done, you can embed the graphs in the system as well, and you can also, they've got a slider here, so I can change values and see what impact that has upon the nature of the system. over time. So that's definitely, in my opinion, the most visual, the best of the competitors we have, and we've simply tried to do as well as this interface to at least do the side that we have to do to be the same as the others, the flowcharts, as well as it's done in Vensim. A couple of little things I might illustrate now. I've got them both running on screen at once. If you want to add an extra element to a summing block here, you've got to come down and add it in. As you can see, this just gets bigger and bigger if you want to add lots and lots of elements together. What we decided to do is say, well, I think operations like addition and subtraction are binary effectively. You're going to add things together or subtract them, so I want to add something else to this block. I don't know that. Let's get rid of that unintentional arrow there. If I want to add something else to here, or either subtract something else from that lot, I can say, let's take a copy of Z here, copy it over here, and wire it up. So I'm subtracting Y plus Y and Z both from whatever the sum is there. So that is, I think, takes up less space than doing this addition of additional elements to a summing block, and it's also more, I hope, more visually appealing than this. So I'm going to be waffling a bit here, sorry about that. I've had a couple of crashes and tried to get this damn thing recorded, so I'm a bit buggered having just spent too much time trying to get this comparison together. But that's where we sit. I think in terms of usability, we are as easy to use as Vensim, but not as completely featured in terms of all the edit commands, and by far lower level of sophistication in terms of all the blocks we support compared to the enormous number of elements that are here. But I think certainly more visual and much more appealing than working with Vensim. And then I hope I brought up, I think I know, there it is. I've logged out of my Unix window here, so let's bring it back in again. Okay, and certainly more user-friendly and more visual than Simulink. So we've got a long way to go before we have anything like the power of the others, but I think in terms of usability, we're up there with the best, which is Vensim.